Hey everyone, I'm Joe Tomasello. Today I'm going to be discussing light time, atomic emission spectroscopy. I'd like to start with a quick overview of what I'm going to talk about today. First, I'll be discussing the speed of light experiment that was ran, followed by the black body emission experiment, and finally finishing up with the line spectrum experiment with a monochromator. My two hypotheses were that Rydberg's constant will be more accurate when accounting for quantized energy levels compared to Bohr's model using reduced mass. This is due to the fact that electronic transitions are included in that equation. The larger mass of deuterium, secondly, will lead to a lower wavelength of emission as the increased mass makes electronic excitation more difficult. So let's start with the speed of light experiment. Measuring the speed of light was pretty straightforward, and we had a diagram by this world-renowned artist to help us out. The experiment was set up using an oscilloscope featuring a light and two detectors. Light was emitted from the light source, goes through the beam splitter window, so the first detector can collect data, and then it's bounced off a mirror, which is placed varying distances away. Then hits a focusing lens and is finally back into the second detector. Both those detectors are attached to the oscilloscope. Shown here on the left is the raw data output of the distances measured and the corresponding times, alongside an output reading from the oscilloscope on the right, which is for the distance at 15 feet. You can note that in the table already you can see a little bit of a trend as when you move the mirror back roughly 5 feet, it leads to kind of a 10 nanosecond increase. But since we have the distance between the mirror and detector, we can double that because the beam goes to the mirror and back and put that over the time of flight in order to get the speed of light c. As you can see by the data, there's a huge error in our first data point at the distance of 1.88 roughly meters. This had to be an issue with measurement, but I couldn't omit this from the data because there are only 5 data points and that would skew everything else. So the average isn't terrible at about 2.7 times 10 to the 8th meters per second. Has a very large standard deviation, as you can see, and overall 10% error, which is okay. But for comparison, we used a different method to determine the speed of light, which is to graph the distance traveled versus the time of flight and using the slope from the line of best fit. And despite how it might seem that this method would actually be better in the presence of an outlier, it actually had a higher percent error than the method of averaging. So going forward, the average value was just used for the rest of the experiment in the speed of light calculations. But determining the speed of light is important. It's a fundamental constant for all other parts of this experiment and all chemistry in general. So let's move on to black body emitters. Black body emitters give off a range of wavelengths when heated, which is interesting because the wavelengths and intensities change as temperature does as well, excuse me. We studied this phenomenon by comparing 3 light sources, incandescent, fluorescent, and LED light bulbs, while also comparing them to 2 measurements of the sun. An ocean optic spectrometer was used with a fiber optic cable and lens, with our good old pal Logger Pro used to collect the data. The fiber optic cable was simply held up to the light bulb, which allowed for a reading in Logger Pro, leading to our data collection. Shown to the right is what our raw spectra output looked like for just the 3 measured sources. 2 equations will be discussed regarding black body radiation, first beginning with the simple Wien's equation. Taking the wavelength of max absorbance of the spectrum and dividing it by this nifty little Wien's proportionality constant, we're able to obtain the temperature of the black body emitter. Shown in the table above is a summary of the different lambda maxes alongside the Wien temperatures calculated. We've seen that the lower the lambda max, so the higher the energy, the higher the temperature of the black body emitter, which makes sense. More energy, more temperature. Second, the more complicated Planck's equation can be used to model the temperature of a black body emitter. This equation was applied to all values of the spectra and a max was obtained. This is through this characteristic wavelength lambda, which isn't necessarily lambda max. So this Planck's black body equation was applied to all wavelengths that were recorded in our raw data. We then obtained the maximum of those Planck's black body values. We could put the max intensity from our raw data over that max Planck's black body value, as you see in the equation below, multiply it times any lambda we want, and we will get an adjusted intensity. This adjusted Planck intensity, when graphed with the original lambdas, any lambda that you calculate it for, will provide a fitting model of the original data, we found that the blackbody temperature for Planck's blackbody was able to be obtained through altering that temperature in order to get the line of best fit, and that's what we record in the table. It'll make more sense once I show you the next slide. As seen, the orange represents the adjusted intensity and the blue represents the original spectra. Fitting was completed by adjusting the temperature in the Planck equation until the fit was mostly correct. And this was the temp that was recorded as our Planck's temperature in the table. Here's an overall summary table. We can see that the sun's outer atmosphere data had the best fit and the highest temperature. I can go back and show you that fit real quick. It's in the bottom right there. That also makes it the hottest black body emitter, as you can see by the data in the table. While the sun's core is 14 million degrees, the data doesn't match this value due to the fact that the light measured from the sun doesn't come from the core. It actually comes from the surface. So it's nothing near 14 million degrees when it's emitted, plus it's really far away from Earth. In general, the Wien equations seem more accurate for most of the spectra, except for that of the fluorescent light bulb, which I can go back and show you in the middle here. Top middle has kind of those sharp peaks on the graph. But overall, when determining the largest temperature of a black body emitter, I thought the Wien temperature showed much better results than the Planck temperature, as it did in fact use the lambda max as opposed to just a fitting method. And the discrepancy between the two is pretty large, ranging between 530 to 550 Kelvin. So again, the Planck equation is just a fit model. Finding the max value of the Wien equation seemed much more useful. All right, we're almost there. So spectral line splitting of this experiment investigated the quantization of energy in which the relationship of the light emitted has a relationship to the change in electronic energy level through the use of something called the Rydberg constant. Niels Bohr later discovered that you can get this Rydberg constant without the use of these electronic energy levels and just using reduced mass. But the goal of our experiment was to compare the two and see which one was truer to literature values. Fortunately for us, our super talented artist picture earlier got the stomach flu, so we'll just have to use a lab manual photo instead to describe this experiment. Light sources passed through a biconvex lens before entering a monochromator. The monochromator was used to disperse light emitted from those discharge lamps, and PMT voltage was adjusted alongside with resolution through altering the slits in the monochromator itself. And I want to note that PMT is photomultiplier tube. This allowed for signal optimization and the detection of 6 atomic peaks for both the hydrogen and hydrogen isotope, which is used to model deuterium for this experiment. I also want to note that we had to use hydrogen for this because the Rydberg equation only works for 1 electron systems. Shown on the right is the entire output spectra, the raw data we have. And it's important to note that the longer the wavelength of transition, the more intense the signal is. And this is due to a great number of particles completing this transition, which makes sense for longer wavelengths. The intensity around 4800 is much bigger than that around 4000, just because of the fact that that is the 4 to 2 transition, as opposed to the anything sub 4000 angstroms is that 9 to 2, 8 to 2, 7 to 2 transition. That 4 to 2 transition is much more probable because it's such a lower energy gap compared to the others. So there's more intensity, more particles can make that jump and will undergo that transition. Now, zooming in on an individual peak, we see 2 peaks, one for hydrogen, one for its isotope, which again is used to model deuterium. I just labeled it as deuterium in this experiment. The hydrogen isotope modeling deuterium appears at a lower wavelength due to its increased mass, which does support our first hypothesis. The line width is slightly broad, just due to thermal broadening, but the main thing is that we can determine lambda max and obtain the energy of each individual transition of the entire spectra. And the trend has shown that the higher the transition state, meaning 9 to 2, as in higher than 4 to 2, the higher energy of the transition, which makes a lot of sense. It takes a lot more energy to jump from 2 to 9 and fall back down than 2 to 4 and fall back down. By plotting the inverse wavelength versus the inverse electronic energy level squared, we're actually able to attain a plot and a slope using Linus. And one more time, our good pal Excel, which models the equation shown in the center below. The slope of the plot is equivalent to the Rydberg constant for our experimental values. The theoretical calculation was completed using the reduced masses of deuterium and hydrogen, followed by Bohr's equation, which is shown on the right. And the calculations, again, were performed in Excel, but this is just a bunch of constants. And the main thing is that it is actually missing those n values as the electronic energy state. So based on the summary of the data, hydrogen had a lower Rydberg constant, both theoretically and experimentally. However, the main takeaway is that the Rydberg constant is much more accurate experimentally than theoretically. The experimental method included the use of energy states, which makes the data more accurate and supports my first hypothesis. Yay. One more thing we want to go over real quick is that the mass of deuterium was calculated using the equation below on the left, and compared to the reference value, which was odd, it came out to exactly 50% error. And the main mistake, I think, stems from just experimental technique, is that actual deuterium wasn't used and that it was a hydrogen isotope. And then shown on the right is the difference in ionization energy between the two methods shown, with some okay agreement of about 11% between the two, but the theoretical energy is likely higher due to its failure to account for the quantized states. So in summary, for the speed of light, our averaging method proved to be much better than the line of best fit method, but again, there was a massive outlier in that data. For our black body emission experiment, Wien's temperature seemed more accurate because it used lambda max as opposed to just a fitting technique with Planck's temperature. And with the line spectrum experiment, the experimental method was much better than Bohr's equation because energy states are quantized and it does model that. And there was a large difference in ionization energy and deuterium mass calculated. And here's some work cited. Thank you.